In part 2 of the nucleophilic substitution of alkyl halides mini lecture series, we'll look into the mechanism of this reaction and try to understand the differences between two different kinds of mechanisms for the reaction. So let's take a look at some of the observations that were made by chemists as they studied this very versatile substitution reaction, where a nucleophile is reacting with an alkyl halide. So when they started with a single enantiomer of a starting material, so a single enantiomer of their alkyl halide, they found that reactions exhibited two types of behavior. Some reactions gave a single enantiomer of the product. And since a single enantiomer will rotate light in only one direction, the product of that reaction is optically active. So when we have a single enantiomer of a molecule, it will interact with plane polarized light to rotate light in a particular direction. A second group of reactions were seen where the products of the reaction were racemic. In other words, there was a mixture of the two enantiomers, a 50-50 mixture of the two enantiomers. The products of such a reaction are optically inactive. They don't rotate the plane of polarized light. And the reason for that is that one enantiomer rotates clockwise, the other counterclockwise, and the 50-50 mixture causes the rotation to be canceled to zero. So our starting material in this case was optically active, it rotated light. Our product was either optically active or optically inactive. A second observation was made, and that is that there were two different trends that were observed from the standpoint of the structure of the alkyl halide. One class of reactions showed that primary alkyl halides reacted the fastest, and tertiary alkyl halides reacted quite slowly. A second set of reactions showed that the primary alkyl halides reacted slowly and the tertiary alkyl halides reacted rapidly. So two different trends of reactivity. And then finally, there were two different types of kinetics situations. One situation was that when they changed the concentration of the nucleophile, they observed that the rate would change linearly with the concentration of the nucleophile. In other words, if you doubled the concentration of the nucleophile, the rate of the reaction would increase by a factor of 2. Another group of reactions showed no dependence upon the structure of the nucleophile or its concentration. If you doubled the concentration of nucleophile in this type of a reaction, it had no influence on the overall rate of the reaction, as measured by the formation of the substitution product. So it's important as we look at the mechanism of this reaction and pretend that we were the early chemists examining this reaction, for us to try to come up with an explanation for why these opposites are occurring with such a similar type of a reaction, simply substitution of a leaving group, of an X, an alkyl halide's halogen, with a nucleophile. Well, the first mechanism that was proposed, or one of the two mechanisms that was proposed, is called the SN2 mechanism. In the SN2 mechanism, our nucleophile reacts with our alkyl halide in a single step to form our product, the substitution product, plus X minus. So this reaction, based upon this mechanism, would be would depend upon the concentration of our alkyl halide to the first power and our nucleophile to the power of 1. So if we double our nucleophile, the rate of the reaction should double. And if we double the concentration of our alkyl halide, the rate of the reaction should also double. This particular reaction occurs with inversion of the stereochemistry of the carbon atom. And to see this a little bit better, let's draw the electron pushing for the reaction. we have a nucleophile attacking the carbon atom, which is partially positive charged. It doesn't approach the nucleophile from the front side where the X atom is. It approaches from the back side, immediately opposite the carbon X bond. So if it approaches in this way, it will come into the cup-shaped cavity formed by the three groups attached to the carbon atom. As the carbon is being attacked by the nucleophile, our X group leaves. And our carbon then gets pushed so that the three groups attached to it are pointing in the opposite direction from where they were to begin with. So one way that I like to describe this is that if we use our hands, where our wrist is the X atom, the structure on the left is cupped to the left. And if we, in our structure of our product, we make our wrist the nucleophile, our product is cupped to the right. And so an analogy here is an umbrella in the wind. If you have a very windy day, the umbrella gets inverted so that the cup is no longer down, protecting you from the rain, but instead cupped up, pointing away, exactly away from where it was to begin with. In this particular reaction, we would expect that the nucleophile could bump into the groups that are on the carbon atom. And as a result, we would expect that as hydrogens in those positions are replaced with carbon atoms, that we might see quite a bit of steric strain between the carbon atoms on the carbon where the X group is located and the nucleophile. And so as a result, this mechanism explains the trend that primary alkyl halides with only one carbon and two hydrogens attached are more reactive than tertiary alkyl halides, which have three carbons attached to the carbon where the halogen is located. So all three of the observations from the experimental results can be explained by this one-step reaction where nucleophile comes in, attacks the carbon, and the X group leaves. A second mechanism, called the SN1 mechanism, was also proposed for the other family of molecules. Now, the SN1 terminology and the SN2 terminology comes from the kinetics, whereas the SN2 mechanism was bimolecular, or order 2, the SN1 mechanism is order 1. And the reason for that is the very first step involves breaking the carbon X bond. This is the rate determining step. And if we look at the kinetics of such a reaction, where that is the rate determining step, we would find out that the rate is dependent only on the concentration of our alkyl halide. The nucleophile doesn't come involved until the second step, which is after the slowest step of the reaction. So this is a unimolecular reaction, and that's the origin of the number 1 in the SN1 descriptor. S stands for substitution, N stands for nucleophilic, the 1 for a unimolecular reaction. Now, being unimolecular, it's a little confusing because this is actually a two-step reaction. So why they call this SN1 with a two-step mechanism versus the other one, which was SN2, which was a one-step reaction, is probably a very good question. So in the very first step of this reaction, we have our carbon X bond breaking. And so if we do our electron pushing on this, our X atom accepts another pair of electrons from what was once our carbon X bond. As a result, the X atom becomes negatively charged. The carbon, in turn, has only 3 bonds to it. It has only 3 valence electrons surrounding it, and it possesses, in this intermediate, a positive charge. We call this a carbo, standing for carbon, cation, meaning that it's positively charged. So this is a reaction intermediate, just like the radicals that we saw in the radical halogenation reaction. In the second step now, our nucleophile reacts with our carbocation to form products. Since the carbon of our carbocation is sp2 hybridized, it is a flattened carbon atom. And our nucleophile can approach from either face of the carbocation, from the left or from the right. And as a result, in our product, the nucleophile can either be attached to the left or it can be attached to the right. In other words, our starting material was cupped to the left, and in our product, our two products are cupped both to the left and to the right. So if we started off with an optically active alkyl halide, a single enantiomer of our alkyl halide, we would end up with both enantiomers of our product. So an optically active starting material becomes an optically inactive product. And we call this process racemization. You get both enantiomers, both hands of the molecule, when you started with only one hand as a starting material. In this particular reaction, the reactivity is the opposite of the SN2 mechanism. We'll see that a little bit more carefully on a subsequent slide. Tertiary alkyl halides actually form a much more stable carbocation, and we call that carbocation a tertiary carbocation. In contrast, a primary alkyl halide forms a much less stable carbocation called a primary carbocation. Let's look at the transition states that are involved in the rate determining step for both the SN2 and the SN1 mechanisms. In the SN2 mechanism, we actually have in the transition state both the nucleophile and our X atom bonded to the central carbon atom. Our carbon has been flattened, and as the nucleophile comes in closer, the carbon begins to break the carbon X bond, and then the three groups attached to the carbon get pushed to the right. And so this is the reason for the inversion at the carbon atom, because the nucleophile actually flattens the carbon and then proceeds to push the three groups attached to the carbon that it's attacking to the opposite side from where they were to begin with. In the SN1 mechanism, our transition state doesn't involve the nucleophile. All it involves is breaking the carbon X bond. So both transition states are highly polar. They both have partial negatives and partial positive charges. And we'll see that this is important from the standpoint of how the nature of the solvent we run the reaction in affects the overall rates of the reaction. So these are transition states in the two reaction mechanisms that we just learned about. Let's look at how the alkyl halide influences the reaction. And this is what we'll often call the alkyl halide, the starting material, the substrate. It's the thing that reacts to form our product. So the first thing is that there are steric effects involved in the SN2 mechanism. As the carbon is being attacked by the nucleophile, that nucleophile experiences steric strain. The steric strain increases as hydrogens on that carbon being attacked are changed from hydrogens to carbon atoms. And so primary is much less crowded than tertiary. Even less crowded than primary is a methyl group, a CH3 group. A second effect is on the SN1 mechanism, where we have a carbocation intermediate. Carbon is a much better donor of electron density than a hydrogen. So as we move from a carbocation that has 3 hydrogens on it to one that has 2 hydrogens and a carbon, to one that has 2 carbons and 1 hydrogen, to a carbon that has 3 carbons on it. The final one, the tertiary carbocation, will be stabilized much more by the 3 attached carbon atoms. And as a result, it's the most stable of the 3 carbocation intermediates. We'll see that this has important implications from the standpoint of how fast this reaction proceeds. We talked about Hammond's postulate in the context of the radical halogenation reaction. In that reaction, we said that the more stable radicals form faster in the bromination reaction. And the reason for that was that since bromination has an endothermic first step that involves the formation of the radicals, our transition state energy is going to be very similar to the energy of the radical intermediate. And if we have a more stable radical intermediate, then our transition state will be more stable, and such a species will be formed faster, because a lower transition state will have a lower activation energy. So let's look at how the energy of our carbocation would influence the rate of its formation. A carbocation has only 6 electrons around it, and as a result, it's going to be an unstable reaction intermediate. It will be higher in energy than our starting material, which is an alkyl halide. In this particular reaction, we're going to substitute an X atom with a water molecule. And as a result, our product is going to be an alcohol and will form a molecule of HX. Well, in this reaction, if it proceeds by a carbocation intermediate, going from our starting material to the carbocation will be an uphill step. If we have a less stable carbocation, the transition state leading to that carbocation is going to have to be a lot higher in energy. If we have a more stable carbocation, the transition state leading to that carbocation is going to have a lower transition state energy. And so we see that tertiary carbocations are more stable than secondary, which are more stable than primary. And as a result, primary carbocations are going to have an extremely large activation energy to form a carbocation. And as a result, primary carbocations will be formed quite slowly. By comparison, secondary carbocations will be formed faster with a lower activation energy, and tertiary carbocations will be formed the fastest because they are going to be more stable, and the transition state energy will resemble the energy of our tertiary carbocation. So this is Hammond's postulate as it's applied to the SN1 reaction. Now, since the first step is the rate-determining step in the SN1 reaction, this first step determines how quickly the reaction occurs. Once the carbocation forms, it very quickly can go over to form product in each of these 3 reactions. So in each one of them, our second step is going to be much faster than our first step. Another particularly reactive substrate is called an alkyl halide. An allylic halide. An allylic halide has a halogen atom attached to an allylic carbon. If you remember, an allylic carbon is one directly attached to a carbon-carbon double bond. These alkyl halides are extremely reactive because in the SN2 mechanism, we get a considerable stabilization of our partial positive charge on carbon by the adjacent carbon-carbon double bond. And as a result, the allylic halides are extremely stable in their transition state when they react with nucleophiles. And as a result, product is formed quite quickly. Allylic halides are also extremely reactive under the SN1 mechanism, because once we've broken the carbon-X bond and formed a carbocation, that carbocation is resonance stabilized. We can push electrons and draw a second resonance structure. And as a result of resonance, our carbocation is going to be much more stable, and its rate of reaction is going to be quite a bit faster than a tertiary alkyl halide. In fact, the trend goes allylic is faster than tertiary, faster than secondary, much faster than primary in the SN1 mechanism. In the SN2 mechanism, allylic is faster than methyl, faster than primary, faster than secondary, much faster than tertiary. So both reaction mechanisms are fast for an allylic halide. Another substrate that's quite reactive is a benzylic halide. It has a halogen attached to a benzylic carbon. A benzylic carbon is a carbon attached to an arene ring. Now, the reason for benzylic halides being extremely reactive is that when we form our transition state in the SN2 mechanism, the adjacent arene ring can stabilize the positive charge on the carbon atom. If it stabilizes that positive charge, then the activation energy for forming that transition state will be lower and the rate of reaction will be faster. In the SN2 mechanism, allylic and benzylic react at nearly the same rate. From the standpoint of an SN1 mechanism, when we break the carbon-X bond and form a carbocation, the adjacent arene ring can stabilize that positive charge, leading to a much more stable carbocation. Since the carbocation is more stable, it's formed faster, and as a result, benzylic alkyl halides are also extremely reactive substrates in the SN1 reaction mechanism. So benzylic and allylic have nearly the same reactivity under both SN1 and SN2 conditions. Let's look now at the effect of our transition of solvents on the energy of our transition states. So as we mentioned earlier, both the SN1 and the SN2 mechanisms have very polar transition states. We're getting charge separation between the nucleophile and the carbon and the X in the SN2 mechanism, and the carbon and the X in the SN1 mechanism. Well, polar solvents will help stabilize polar transition states. And as a result, any polar solvent is a good one for running SN1 and SN2 reactions. They're much faster in those solvents compared to nonpolar solvents. Some examples of some nonpolar solvents are hexane, which only has carbon-hydrogen bonds and carbon-carbon bonds in its structure, benzene, which similarly has carbon-carbon and carbon-hydrogen bonds, and carbon tetrachloride, which has no net dipole moment as a result of cancellation of the 4 carbon-chlorine bond dipoles. So nonpolar solvents will cause a very slow SN1 and a very slow SN2 reaction mechanism. Some of the best solvents for the SN2 reaction are shown on this slide. Tetrahydrofuran, acetone, dimethyl sulfoxide, and NN-dimethylformamide. It's important for you to remember the acronyms for these molecules: THF, DMSO, and DMF, in case you see them under the reaction conditions for one of these reactions. All 4 of these solvents possess dipole moments, and as a result, they are polar solvents. Another feature of these solvents is that they have no OH or NH bonds in their structure. As a result, they are not hydrogen bond donors. They do possess lone pairs on the oxygen atoms in each of the structures, and so they are good hydrogen bond acceptors, but not hydrogen bond donors. They only weakly solvate the nucleophile, but they strongly solvate the counterion, sodium or whatever the counterion might be, to our nucleophile. And as a result, the nucleophile behaves as if it is not surrounded by solvent molecules, and those solvent molecules do not inhibit how quickly the nucleophile might react with an electrophile. So doing it cartoon, we will have our metal salt and our nucleophile minus. Our cation is well solvated by these solvent molecules, but our nucleophile is only poorly solvated, and as a result it can react with our alkyl halide much more readily, leading to the substitution reaction. This slide shows some of the best solvents for an SN1 reaction. They also possess dipoles, and so as a result they are polar, just like the SN2 solvents. In contrast with the SN2 solvents, though, they all possess OH groups in their structure. These are hydrogen bonding solvents, very good at being able to hydrogen bond to a pair of electrons. We call these polar protic, while the other solvents, the ones for SN2, are called polar aprotic. If we draw a cartoon, our metal salt, metal cation, nucleophile minus, both the metal salt, the metal cation, and our nucleophile are strongly solvated by these solvents. In fact, the nucleophile benefits by hydrogen bonding from the hydrogen atoms in these solvents to the lone pairs on our nucleophile. And that results in our nucleophile becoming extremely stable. And being extremely stable, it is extremely unreactive. If the nucleophile is unreactive, then our alkyl halide can actually break its carbon-X bond with the nucleophile not being involved. And so these solvents tie up the nucleophile, prevent it from reacting directly with our alkyl halide, and as a result they favor the SN1 mechanism. In the SN1 reaction, very often these solvents are also our nucleophile, so that instead of having some other nucleophile react, the solvent itself can become our nucleophile. Each of the oxygens in these molecules possess lone pairs, and as a result they can be nucleophiles toward an alkyl halide. Let's look now at the structure of our nucleophile and how it influences the reaction. In the SN2 reaction, it's exceedingly important that our nucleophile be a good Lewis base. It has to donate a pair of electrons to our alkyl halide in order for the reaction to occur. As a result, we want our nucleophile to be a good electron pair donor, a good Lewis base, but we don't want it to be too strong of a base. If it becomes too strong of a base, it could start undergoing an elimination reaction instead of substitution. In general, negatively charged nucleophiles are much stronger nucleophiles than our neutral nucleophiles. So if we look at a pair of nucleophiles like water and hydroxide, water is a weaker nucleophile by far than is OH minus. So the nucleophile is not important, though, in the SN1 mechanism. If we have a very poor electron pair donor, in other words, an atom that is very poor at being able to donate its pair of electrons to another atom, it will be actually favoring the SN1 mechanism. Whereas if the nucleophile is a good electron pair donor, it will strongly favor the SN2 mechanism. As a result, if we have the conjugate acids of nucleophiles, they're going to be much weaker bases because they have a proton on them than the nucleophiles themselves. And so species like H nucleophile, where we have the conjugate acid of a nucleophile, favor quite strongly the SN1 mechanism. If you remember from the slide on the solvents for the SN1 mechanism, all of those had a hydrogen attached to a species that we had seen in part 1 as being a nucleophile. OH minus, carboxylate, those are all the conjugate bases. Even alkoxide, its conjugate acid is an alcohol, and that was one of the polar protic solvents that we saw on an earlier slide. So our solvent can be our nucleophile in this case. Let's look now at the thing that leaves the carbon atom. We call that the leaving group. Our leaving group is best when it wants to leave with its pair of electrons. As a result, we want to have the negative charge end up being quite stable. And negative charges are quite stable when they're dispersed over a very large surface area. So iodide, on the bottom right of the periodic table, is an exceedingly large atom, and as a result the negative charge is very diffuse over the large surface area of I- and quite stable. So I- is one of the best leaving groups. Slightly worse of a leaving group, but still quite good, is a bromide. It's smaller in size than an iodide, and so the negative charge is more concentrated on the smaller surface area of Br-. Compared with chloride, bromide is an exceedingly good leaving group. Chloride is a very poor one. We have a small surface area over which we distribute a negative charge. Fluoride is a lousy leaving group, as is hydroxide, OH-. And the reason for this is that these are very strong bases. They like to hold on to things, to be able to be bonded to a proton. And for the same reason, they form very strong bonds with carbon atoms. We'll see that two other leaving groups that are really quite good are a water molecule and a species called tosylate, or paratoluene sulfonate. It's often given the generic name, or the common name, tosylate, and it simply refers to this anion with an arene ring and a sulfur with 3 oxygens on. This is a resonance stabilized anion and is really very stable and is an exceedingly weak base. And we'll see ways of making an OH group, OH- leave, by either converting OH- to a water molecule or by making the OH group into a good leaving group by modifying it into a group that has this tosylate as part of its structure. So for both the SN1 and the SN2 mechanisms, it's really critical that we have a good leaving group. In the SN1, it's even more important because our nucleophile is not assisting the departure of the leaving group. The leaving group must leave in the rate determining step all by itself to form a carbocation intermediate. In the SN2 mechanism, the nucleophile assists the departure of our leaving group, and so the quality of the leaving group is somewhat less critical in the SN2 mechanism.